Somewhere in a laboratory in Palo Alto, a company just made a call that could quietly upend the internet as we know it, and hardly anyone is paying attention. There was no explosion, no press conference with fanfare, just one unusual decision. Rather than chasing colder freezers and stronger magnets like everyone else in the quantum computing race, this company chose to stake everything on light. Simply light. Photons. The very particles that carry your streaming shows through undersea fiber optic cables. And here's the piece that should genuinely rattle you. If this gamble works out, every classical computer on the planet, every supercomputer, every server farm, every machine humans have ever constructed will have no way of keeping up with where this thing is heading. Not merely slower, not just trailing behind, fundamentally and mathematically unable to catch up. That company is PsiQuantum, and what they're building at this very moment could be the most important piece of hardware that almost nobody outside a tight circle of physicists and defense contractors has ever encountered. Let's rewind for a moment, because to grasp why this matters, you first need to understand what nearly every other quantum computing company on Earth is doing instead. Google, IBM, most of the big names you've seen splashed across headlines, they construct their qubits, the fundamental units of quantum information, using tiny superconducting circuits. To get those circuits to behave quantum mechanically, they must chill them down to roughly 15 millikelvin. That's colder than deep space, colder than the empty stretches between galaxies. It requires a device called a dilution refrigerator, an enormous, delicate, chandelier-like contraption, just to keep the qubit stable enough to do anything meaningful. It's costly, it's fragile, and scaling it up to millions of qubits is an engineering headache that some scientists genuinely question is achievable with today's methods. PsiQuantum examined that whole strategy and essentially said, "We're not doing that." Their qubits aren't miniature circuits held near absolute zero. Their qubits are photons, single particles of light traveling through silicon chips at room temperature. No dilution refrigerator needed for the core computing work. No exotic super-chilled setting. Just light channeled through waveguides carved into silicon, the same type of silicon that makes up your phone's processor. This isn't some minor technical preference. It's an entirely different philosophy for constructing a quantum computer, and it reshapes nearly everything about what's achievable. Here's why that's such a big deal. Photons hardly interact with their surroundings. That might sound like a minor footnote, but it's actually the whole reason this method could work at massive scale. A photon moving through fiber doesn't really notice the room's temperature. It doesn't get jostled by stray heat the way a superconducting circuit does. That means photonic qubits can, in theory, maintain their quantum state with far less interference from the environment. They can achieve this without the brutal infrastructure expense of cryogenics. You could, at least conceptually, run one of these systems in something resembling a normal data center room, rather than a physics lab built around a giant refrigerator. PsiQuantum's central piece of hardware is called Omega. It's a silicon photonic chipset, and the company has been developing it alongside Global Foundries, one of the world's largest semiconductor manufacturers, at a flagship facility in Malta, New York. Consider for a second what that partnership really means. PsiQuantum isn't attempting to invent a brand new manufacturing process from the ground up in some experimental garage setup. They're tapping into trillions of dollars of existing semiconductor infrastructure, the same infrastructure that has spent decades mastering how to mass-produce chips affordably and reliably. That's a calculated strategic move, and it's one of the reasons serious players in the industry take PsiQuantum seriously, even though the company has traditionally kept its exact progress under wraps. Now let's talk about scale, because this is where things start sounding almost impossible to believe. PsiQuantum has publicly said they believe they need somewhere around 1 million physical qubits to construct a genuinely useful, fault-tolerant quantum computer. 1 million. To put that in perspective, the most advanced superconducting quantum computers from other major players currently operate with qubit counts in the hundreds or low thousands. PsiQuantum's wager is that photonic qubits, built atop existing chip fabrication technology, can scale toward that million-qubit goal in a way superconducting approaches simply can't, because you're not battling the physics of large-scale cryogenic cooling. Instead, you're up against a different set of engineering challenges, ones the semiconductor manufacturing industry has already gotten remarkably good at solving. That doesn't mean any of this is simple. Photonic quantum computing carries its own brutal technical hurdles, and pretending otherwise would be dishonest. Photon loss is one of the biggest. Every time a photon passes through a waveguide or an optical component, there's a chance it just gets absorbed or scattered and vanishes. Lose too many photons and your computation collapses. Reliably generating single photons on demand, indistinguishable from one another, is also notoriously tricky. And building error correction systems that function for photonic setups forced PsiQuantum's own researchers to develop something new, an architecture called fusion-based quantum computing, which relies on entangling measurements between small resource states rather than depending purely on direct qubit-to-qubit gates, the way superconducting systems typically do. This architecture was built specifically around light's particular strengths and weaknesses as a computing medium. So why does any of this mean classical computers can't keep pace? This is the part people tend to gloss over, and it's really the heart of the whole story. A classical computer, however powerful, represents information as bits, ones and zeros, one state at a time. A quantum computer represents information in superposition, meaning a system of qubits can explore an enormous number of possible states all at once. That state space grows exponentially with the number of qubits, not linearly, but exponentially. Every additional qubit doubles the space of possibilities the system can represent simultaneously. That's why quantum computers aren't just faster versions of classical computers. They're a completely different category of machine for certain types of problems. And that's why you can't simply throw more classical processors at the issue to keep up. Once you hit a large enough qubit count, simulating a quantum computer on classical hardware would demand more memory than there are atoms in the observable universe. That's not an exaggeration. That's the literal math. This is precisely why the security world watches PsiQuantum so closely. Much of the encryption protecting your bank account, your medical records, and honestly the entire backbone of global digital infrastructure depends on mathematical problems that are extremely difficult for classical computers to crack, like factoring enormous numbers. RSA 2048 encryption, one of the most widely used standards on the planet, rests on exactly that kind of problem. A sufficiently powerful, fault-tolerant quantum computer running an algorithm called Shor's algorithm could, theoretically, break that kind of encryption in a time frame that would be utterly impossible for any classical supercomputer, even one running longer than the universe has existed. PsiQuantum's aggressive push toward large-scale error-corrected qubits has made them one of the company's national security researchers name as a genuine contender to hit that threshold ahead of most competitors, which is exactly why governments have stopped treating this like a science experiment. And the government interest here isn't speculative. It's already very real and very well funded. PsiQuantum has secured backing from DARPA, the very agency that helped create the Internet, as part of the U.S. 2QC program, which is specifically focused on evaluating whether a real architecture from a company like this could deliver genuine economic and strategic value. The company also raised over $1 billion in a single Series E funding round, and it broke ground on a large-scale quantum computing site at the Illinois Quantum and Microelectronics Park in Chicago. On top of that, the Australian government backed a deployment site in Moreton Bay, Queensland, with roughly $940 million in support, a staggering vote of confidence from an entire national government in a technology that hasn't yet been proven at full scale. PsiQuantum has been quietly forming partnerships that hint at where this technology is actually headed once it works. They've teamed up with NVIDIA, focusing on silicon photonics and AI supercomputing, which tells you something important. This isn't just about someday cracking encryption. It's about the intersection of quantum processing and the AI infrastructure boom already reshaping the entire tech industry. They've also worked with Airbus and Lockheed Martin, aerospace and defense giants interested in the kinds of complex materials science and optimization problems a fault-tolerant quantum computer could eventually help tackle. Problems currently just out of reach for classical supercomputers, no matter how much computing power you throw at them. There's also a notable leadership change worth mentioning, because it reveals where the company believes it stands in its own journey. Victor Peng, who previously played a major role in a massive $50 billion acquisition in the semiconductor world, stepped in as interim CEO, while co-founder Jeremy O'Brien moved into the role of executive chairman. That kind of shift, bringing in someone with deep operational and manufacturing scale-up experience, usually signals a company transitioning from pure research and development into a phase centered on execution and deployment. PsiQuantum has stated its goal is to deliver what it calls the world's first utility-scale quantum computer. So the company set an internal target date in February 2026 for this leadership transition to align with that next phase of large-scale deployment. Let's talk about where this technology actually leads once it works, because the applications are honestly wilder than most people expect. PsiQuantum has built a software platform called Construct, designed specifically for developing fault-tolerant quantum algorithms before the hardware itself is even fully operational. That's an unusual move. It means the company isn't just racing to build a machine, it's simultaneously making sure that the moment that machine switches on, algorithms are already ready to run on it. The target industries aren't abstract either. Energy companies want quantum computers to model complex chemical reactions for better batteries and cleaner fuel production. Pharmaceutical companies want to simulate molecular interactions currently too complex for any classical supercomputer to accurately model, which could dramatically accelerate drug discovery. Material science researchers want to design brand new materials atom by atom, something essentially impossible to brute force classically once you pass a handful of atoms. Finance firms are interested in portfolio optimization problems that scale in ways classical computers genuinely struggle with. None of this is science fiction speculation. These are the specific use cases PsiQuantum and its government partners have publicly pointed to as the reason billions of dollars are already flowing into this bet. It also helps to understand the origin story here, because it explains why PsiQuantum took such an unusual path in the first place. The company was founded in 2016 by Jeremy O'Brien, Terry Rudolph, Peter Shadbolt, and Mark Thompson, a group of quantum physicists who had spent years studying photonic systems at the University of Bristol and Imperial College London before launching the company. These weren't generalists who stumbled into photonics on a whim. They were specialists in light-based quantum systems who surveyed the entire landscape of competing approaches and made a calculated bet that photons, not superconducting circuits, not trapped ions, were the path capable of actually scaling to the millions of qubits a truly useful machine would need. In 2019, they locked in their manufacturing partnership with Global Foundries, years before most of the public had even heard the term quantum computing outside of movies and science headlines. It's also worth placing PsiQuantum's approach alongside the handful of other serious photonic players, because this is genuinely a competitive field, not a solo effort. Xanadu, based in Toronto, has taken a different technical route using squeezed light and continuous variable quantum computing, and their Borealis processor has already demonstrated something called quantum computational advantage using a task called Gaussian boson sampling, meaning it solved a specific problem faster than any classical computer realistically could. Quandela, a French company, has focused heavily on building extremely high-precision single-photon sources and an open-source software toolkit called Percival, making photonic quantum computing more accessible to researchers who don't have access to million-dollar labs. Even China has explored photonic approaches, most notably through the Zhuzhong experiments, which demonstrated a specific, narrow kind of quantum advantage using boson sampling techniques, though notably not a universal, general-purpose quantum computer the way PsiQuantum is attempting to build. What sets PsiQuantum apart in this crowded field is the sheer scale of its ambition. It isn't trying to build a research demonstration or a narrow proof of concept. It's trying to build a fully error-corrected, general-purpose, million-qubit machine using manufacturing processes borrowed directly from the existing global semiconductor industry. That manufacturing detail deserves one more moment of attention because it's genuinely the clever part of this whole strategy. Building a quantum computer from scratch using brand new exotic materials and untested fabrication techniques is unbelievably expensive and slow. PsiQuantum instead asked a different question. What if we design our photonic qubits to be compatible with the same fabrication lines already churning out billions of computer chips every year? That decision means every improvement the semiconductor industry has made over decades, tighter tolerances, higher yields, lower defect rates, automatically benefits PsiQuantum's roadmap too. It's a bit like deciding to build a spacecraft using the same assembly lines that already mass-produce cars, instead of handcrafting every single part from raw materials in a garage. That one strategic decision is arguably why serious government agencies and multi-billion-dollar aerospace companies are willing to place such large bets on a company that, until fairly recently, most people outside the field had simply never heard of. Of course, it would be irresponsible to present all of this as a guaranteed outcome. Healthy skepticism matters here. PsiQuantum has historically been extremely secretive, choosing not to publish the kind of detailed, incremental public roadmaps that competitors like IBM or Google regularly release. Some experts argue this secrecy makes it hard to independently verify how close they actually are to their milestones. The technical risk in scaling any photonic system to 1,000,000 qubits remains enormous, and photon loss, precise timing synchronization across massive chip arrays, and manufacturing yield are all serious, unsolved engineering problems. Other companies pursuing photonic approaches, like Xanadu with its work on Gottesman-Kitaev-Preskill states for error correction, and Quandela with its high-precision single-photon sources, show this is a genuinely competitive and unsettled race, not a solved problem with PsiQuantum as the only player. But here's the thing that should stick with you after this video ends. Even accounting for all that uncertainty, the underlying physics argument doesn't change. If a company, any company, manages to build a stable, error-corrected quantum computer with enough qubits, the exponential nature of quantum state spaces means classical computers won't simply be outpaced. They'll be left in a completely different category of machine, the way a horse and carriage exists in a different category from a jet engine. You can't brute force your way across that gap by building bigger data centers or faster processors. The math itself closes that door. And PsiQuantum's decision to build that future out of light instead of exotic cold matter is exactly why so many serious researchers, defense agencies, and now entire governments are paying such close attention to a quiet company in Palo Alto that most people have still never heard of. There's also an important nuance worth adding here, because it keeps this story honest rather than turning it into pure hype. While photonic qubits themselves can operate without needing to be near absolute zero, that doesn't mean the entire system is completely free of cryogenics. Certain supporting components, like some single photon detectors, still benefit from cooling to improve their precision and reduce noise in the readout process. So when people say photonic quantum computing is a room temperature technology, the honest version of that claim is that the core computation and qubit manipulation can happen without the massive dilution refrigerators superconducting systems absolutely require, even if some peripheral hardware still uses cooling to sharpen performance. It's a meaningful difference in complexity and cost, but it's not quite as simple as photons never touching anything cold anywhere in the system. The two physical deployment sites PsiQuantum is building right now tell you a lot about how seriously governments are treating this technology. In Chicago, the company broke ground at the Illinois Quantum and Microelectronics Park, a site specifically designed to host large-scale quantum infrastructure alongside supporting research facilities, positioning the American Midwest as a serious hub for next-generation computing rather than just Silicon Valley. On the other side of the planet, the government of Queensland, Australia committed roughly $940 million to bring a PsiQuantum facility to the city of Moreton Bay, an enormous public investment for a piece of technology that hasn't yet been fully proven at scale anywhere in the world. When two different national governments are willing to put that kind of money behind a single company's engineering roadmap, it tells you they aren't treating this as some distant academic curiosity. They're treating it as critical infrastructure worth securing early, the same way countries once raced to build early telecommunications networks or nuclear research facilities. Because being early to a foundational technology often determines who benefits most once it matures. This is also exactly why cybersecurity experts aren't waiting around for PsiQuantum or anyone else to actually finish building a working million-qubit machine before taking action. Governments and major technology companies worldwide are already transitioning to what's called post-quantum cryptography, meaning new encryption standards specifically designed to stay secure even against a future fault-tolerant quantum computer. The National Institute of Standards and Technology in the United States has already finalized several post-quantum encryption algorithms, specifically because of threats like the one PsiQuantum represents. Think about what that means for a moment. Organizations are rewriting the security foundations of the entire internet today, years in advance, because of a machine that doesn't fully exist yet, purely because the mathematics of what happens once it does exist is considered too dangerous to leave unaddressed. That is an almost unprecedented level of proactive global coordination around a single emerging technology. And PsiQuantum's aggressive roadmap is one of the biggest reasons that coordination is happening on the timeline it's happening on right now. So the next time someone tells you quantum computing is still decades away and not worth thinking about, remember this. Real money, real government contracts, real semiconductor fabs, and real physicists with real timelines are already treating this as an active near-term race, not a distant hypothetical. Whether PsiQuantum wins that race or one of its competitors does, the underlying shift is coming, and it won't announce itself with a warning. It will simply arrive one day as a machine that can do in minutes what would take every classical computer on the planet longer than the universe has existed to finish. That's not science fiction. That's where the silicon photonics roadmap is already pointing right now. If this kind of deep dive into the technology quietly shaping the next decade is something you want more of, make sure you hit that subscribe button so you don't miss what comes next, because this story is only getting started. And if this blew your mind even a little bit, drop a like before you go. It genuinely helps this channel keep making videos like this one. Thanks for watching, and I'll see you in the next one.